PowerPoint. Okay. Now, I suppose what you see is the PowerPoint slide, right? Okay. So what we see here is that if you can capture the data and explain it in terms of the cumulative distribution, you can do a forward calculation of the probability, and you can do an inverse calculation to simulate the value itself. With this, it allows us to perform different types of things. We can do queuing system. We can model the queuing system and determine whether modifying configuration of the queue would affect the results or not. We will be able to do projection of the system. If we add another server, would that increase the performance? Would that increase the throughput of the systems? Or if we can think about the service queue, like a bank teller, if we have another counter open, would that reduce the length of the queue in the queuing system? This by using understanding distribution, we can apply this to perform that as well. We can do the projection of inventory and supply chain to know the size of order that or the purchase that would happen. We can estimate the reliability of the device and other things. These are the use case. Right, let's take a look at the queuing system. In the queuing system, you have the customer arriving, and there will be inter-arrival time. In this case, for the inter-arrival time, this can be modeled as exponential distribution. Customer would come in to the queue, and then the first customer will got served by servers, and there will be this processing time. Processing time is usually modeled as exponential distribution as well, but it doesn't have to be that way. It can be normal distribution. If you know that the time required to process would be about like fixing computers require like 1 day to do that, or maybe more, then you can have different distribution to model this these time steps. Then customer will depart. Right, queuing system can be used to explain lots of things like servicing, machine broke down, the car drive-through service, and other things. So we can use the statistical model to model the inter-arrival time and the service time. Usually, exponential distribution is used for the inter-arrival time, or the service time if it's completely random. Like you don't know the types of order that coming in. It can be fast, can be slow. So this can be used as the exponential distribution. It can be normal distribution if you know that you require about 3 hours to process, more or less a bit. Or you can use the truncated normal distribution, like normal distribution, but we restrict it to like not more than 3 days. So that's the truncated version. The Weibull and gamma distribution can be used as well, but mostly it will be in terms of using exponential part of the Weibull and gamma. Right. So that is for the queuing system. Right? You can see that we can use it to model times. For the inventory and supply chain, what are inventories and supply chains? Inventories, I'm referring to here is inventory management, like how many stock, how many items you want to store at the counter. For the supply chains, I'm talking about the transferring of goods between maybe warehouse to the store, right? So there are a number of parameters, that might be related to the random distribution. So there are at least here in this example, this value, like the number of units demanded per order. Like customer coming in want to purchase, the number of units the customer want to purchase will be random variable. It can be one, it can be multiple items at a time. The time between demands, the time between purchase, this is also random variable. By now, you might guess that it might be exponential, right? The first one will probably be Poisson distribution, right? Number of count. And there will be this lead time. What is lead time? In supply chain terms, lead time refers to the time required for, well, let's say you have a store and you have a warehouse, the time required for when the store want to order something, the store have to place order, maybe to the house or maybe to the factory. And then those warehouse factory or the provider need to transfer the goods to the store. Lead time refers to the time that the store requests until the time that the item arrives. So that lead time can be random variable as well. And modeling that lead time would allow the store to create, to do a lot of things like creating inventory management system, doing forecasts and lots of other things. Okay. Distribution model for different types of for parameters like lead time, you can use the gamma distribution to model the lead time. The demand distribution can be Poisson, which is very simple. It can be binomial, negative binomial, which has longer tail than Poisson. That means for longer tail, it means a large size of demand, you have small size, a large size of demand, and you want to model them all together, then you can use the negative binomial distribution. Or you can use a geometric distribution like this one, geometric distribution. This is special case of binomial distribution that there is like at least one demand that has occurred. Right? This is like similar to the negative binomial. So you can see that for Poisson binomial, negative binomial, and geometric, it kind of creating something like for Poisson, you got a shape like this one. Negative binomial is like binomial distribution, but you have longer tail. Geometric like this, a geometric distribution. You have mostly a cluster to low value, at least one, but it's kind of having long tail. So these different types will reflect different process. Doesn't mean that you see the data and then you can pick just one out. Sometimes you need to see the constraint as well in order to know the proper distribution to be used to model that. But this is not empirical. These are theoretical distribution. The benefit and pro and cons of using distribution in theoretical sense and empirical sense is like this. Empirical sense, you need data, lots of data to be certain. Theoretical sense, you just need parameters. You can estimate parameters from data. Once you get those parameters from data, you can generate a lot of value out of that. But the cons of theoretical distribution is this. You need to test for fitness, whether the distribution is good or not good, right? We are not going to cover that here in this lecture. For reliability and maintainability of the device, there is this time to failure. Like when you purchase your new equipment, there will be a warranty time that this equipment should not fail up until this time. So time to failure is used to explain a lot of things like time to death, time to broken down, time until the next visit in this sense. So what types of distribution can be used to model time? First, surely the exponential distribution. Like if the failure occur at random, we can use the exponential distribution to model that. That is mostly, it would kind of cluster to the low value, but sometimes having high value. The gamma distribution, if there is some types of redundant standby redundancy, each component has exponential time to failure. You can use the gamma distribution. So what does it mean? It means that each component would have exponential TTF, but you have multiple components to replace one another, and that time to failure of the system would be gamma distribution. The Weibull distribution use is when in the case that failure is due to the most serious number of defects in the system. If there are a lot of error occur, then the system would fail. A lot of failure, the system would fail. Then the Weibull distribution is used. A normal distribution is the failure that are due to wear. So normal distribution is used to model the warranty failure, that you want to know if you use it for a lot of time, it will fail. I think there's the Galaxy Flip or Galaxy Fold test, right? So normal distribution is used to test that fold, right? Number of times that it will break down, if due to wear, due to your usage, like that. So in summary, in terms of this lecture, what you see is that when you take a look at the process, you need to think about it probabilistically. You need to think about the randomness in that. Actually, right now, there are events occur all over the world, as you see. And you can see that there are certain probabilistic randomness related to that. And what we have reviewed here, we have reviewed the probability distributions, and we see the applications of the distributions that can be used. We see how we can implement it in R. And the next time, we will take a look at the way that we can further implement the simulation based on these distributions. All right. Now it's time for the lab, which since we are not in the class, this think of it like your lecture, like your homework. Right? Need to submit this before next time to the LEB2 system. All right. You need to select one numerical column from your data point. Your data set. The data set that you can be any data set that you have right now. And then plot the probability distribution, plot the CDF, and sampling 10 value from your distribution using the inverse CDF way that I use. Okay, any questions about the lab or about the lecture? Please feel free to ask.